All right, so hey man, we are cruising in this Math 202. We are just about done with chapter, whatever chapter we're on. I think it's 13, which leaves just one more to go. But I want to let you know that I'm going to do things slightly out of order. So we just got done talking about spherical and cylindrical and how we can convert to those and use those. And so I think it's really natural to move on to the variables. Let me look at my book real quick, tell you the numbers. So the spherical and cylindrical stuff is section 5.5. And so we're going to jump straight to 5.7, which is just talking about any generic kind of transformation, like what we can do, not just for things like polar and spherical and all that. We will come back, don't worry, I am going to come back to 5.6, which are some applications of triple integrals and double integrals. So we'll definitely do that, but just want to let you know, I'm going to jump out of order just a little bit. So today we're going to, kind of wrap up the cylindrical spherical discussion, but then go to the, well, what if we want to transform it in another way? Because maybe it'd be better to have, instead of, like circular regions, maybe we have pentagonal regions, or maybe we have quadrilaterals, or, who knows? So we'll talk about that. But I do know that there are a couple of questions I just saw in the chat box. Eduardo asked about homework 5.5, number 9. Seamus is seconding that with number 3. So we'll definitely look at some homeworks. And then I'll address the question that Victor had. He just put in the chat box a little bit ago about how do you tell whether you want cylindrical versus spherical. And so we'll definitely address that. But let's start with homework questions. So I see from 5.5, 3, and 9. Any others out there we want to look at? Okay, so it looks like just 3 and 9 are being requested, but I'm going to guess that by the time we're done with this, we'll probably also address Victor's question. But if I don't in the course of homework, please, Victor, let me know, remind me, and we'll be sure to talk about how to tell when one is better than the other. All right, so let me go ahead and share my screen. So let's start with question number 3. All right, so again, yours is going to be similar to this, not necessarily identical, but similar. All right, so we've got find the volume of the solid bounded below by the circular cone and above by the sphere, x squared plus y squared plus z squared equals 8z. So this is actually very similar to the example that we did in class, the one that was that we attacked with cylindrical and with spherical. It's slightly different because this sphere isn't actually centered at the origin. Do you know what about it tells me it's not centered at the origin?
The 4?
Not the 4. The 4 is part of the cone equation. And all that does is change the steepness of the cone. You know what I mean? Like
yeah, like the angle of which.
Yeah, so yeah. Is it a really steep cone? Is it a flat cone? I don't know if you see my hands.
Yeah.
But that's what that 4 is doing. But look at the sphere equation. What's different about that as opposed to the one?
Yeah, the 8z.
Yeah, that 8z. Because of the fact that there's a letter over here, that tells me that this thing is not centered at the origin. Because I would have to move that 8z over, complete the square. It would give me like a z minus 4 quantity squared. So I know it's not centered at the origin, but it's really kind of the same idea. It's just that cone may not be exactly centered on the sphere. Okay, so this could be like a lopsided ice cream cone, but we're going to approach it pretty much the same way. So let me go ahead and I'm just writing down these equations so that I can go to the whiteboard. Okay, so this is the cone is the bottom and the sphere is the top. All right, and so all we're finding is volume, which means we just have to integrate 1 dV. All right, so, oops, that is not what I meant to do. But here we go. Okay, so here's a whiteboard. So let's look at this thing. So we've got the top. That's given by x squared plus y squared plus z squared equals 8z. The bottom is the cone. Z equals 4 square roots of x squared plus y squared. All right, so if we want to start setting up this integral, it's going to be a triple integral over the space, whatever the space is. We are going to do a dv, just a 1 dv. All right, now, in terms of the first bounds, I'm going to suggest we do dz first. So I'm going to put here dz dA so that the double integral is over whatever the region that we're looking at. And so in terms of our bottom and our bottom is going to be 4 square roots of x squared plus y squared. And then the top, ooh, what's the top going to be? You ready for some fun with this one? We got to solve this for z. And since we've got multiple z's, this is a quadratic. So notice that this is quadratic in z. We got z squared minus 8z and then plus a constant. So if we're going to solve this, it'd be z equals 8 plus or minus the square root of 64 minus 4 times x squared plus y squared, all divided by 2. So this is the quadratic formula with a equals 1, b equals -8, and c equals x squared plus y squared. I can factor out 2 from the square root by dividing out a 4. So I get 16 minus x squared minus y squared over 2. And now those 2's cancel. So that's the equation of the sphere solved for z. Before we decide which one goes on top, notice that we do have a plus or minus, but that shouldn't surprise you. What are the plus and minus differentiating? What is the difference between those?
Top bound and lower bound.
Yeah. So this would be the top half. The plus is the top half of the sphere. The minus is the bottom half of the sphere. Right? Because the sphere is not a function. It fails the vertical line test. So we're either going to use the plus or the minus. So which one do you think we want to use, the plus or the minus?
Plus.
Yeah, so a couple of you are saying plus in the chat box, and I think that was Seamus who just yelled it out. But yeah, plus. And as Victor said, because it's the top, And think about this cone. These z's are always positive, right? No matter what we plug in for x and y, the z from the cone is positive. So if we need to be above it, we need to have positive numbers. And we need to make sure that it's positive. We're going to use the plus. Okay, so this is going to be the 4 plus square root of 16 minus x squared minus y squared. Okay, well, there's the bounds on z. But now to get the bounds on x and y, we need to know the region over which this shape lies. I know that already some of you are like, Jesus, just go to cylindrical or spherical already. We will, but I want to kind of walk through it in rectangular just so you can see what kind of nightmare we're in for if we don't switch. So how are we going to figure out what region we're going to integrate over? How do we figure out
where the
shadow?
cone intersects the sphere? It's going to be a circle.
Yeah, we need to look at these and see where the intersection is. So I'm going to go ahead and just plug this in for the z's. So we're going to get x squared plus y squared plus 4 minus the square root of x squared plus y squared squared equals 8 times 4 square roots of x squared plus y squared. And let's see if we can just make that a little bit prettier. So this is going to be 17x squared plus 17y squared equals 32 square roots of x squared plus y squared. Okay, well, that's 17 times x squared plus y squared equals 32 times x squared plus y squared to the 1/2. Let's divide by that x squared plus y squared to the 1/2. So we get x squared plus y squared to the 1/2. That's going to equal 32/17. So if we square both sides, because I'm too lazy to square it out actually, we're going to get x squared plus y squared equals 32/17 squared, which is a circle. It's a circle centered at the origin whose radius is 32/17. All right, well, then that means if we were to change this to a, say, dy dx, then let me erase the r. So then the bounds on this are going to be y equals minus square root of 32/17 squared minus x squared. The upper bound is the positive square root of 32/17 minus x squared. And then the x's are going to go from minus r to plus r. So from minus 32/17 to plus 32/17. All right, so this is what it would look like in rectangular. And hopefully you're all on board with no. Just no, I'm not going to do that. So let's think about our options otherwise. So since we're in 3D, cylindrical or spherical are both good. So maybe this will actually be a good way to address Victor's question of how do you know which one you want to go for. Let's start by thinking about just going to rectangular. Or sorry, to cylindrical. Sorry, we're in rectangular. So let me erase some of this nonsense because we don't want that big, horrible looking thing. And I'm going to erase this. I'm going to keep the equation of that circle where they intersect just because that's potentially useful to know what R is, right? The region over which where we're integrating. So that guy's R. So let's go to cylindrical. So what we're going to do then is we'll go with an R dz dr d theta. So let's think about converting these things into cylindrical. So the bottom, what's that going to be in cylindrical? Z equals what?
4r.
Good. 4r. Square root of x squared plus y squared is the square root of r squared, which is r. So beauty. Okay, what about the top surface?
4 plus root 16 minus r squared.
Yeah, let's come back over here. If we remember, our x squared plus y squared is actually r squared. Then this is going to be 4 plus the square root of 16 minus r squared. Now, still not pretty, right? It's definitely not pretty, but it's way better than what we had before, especially with this lower bound. But this isn't where the beauty really comes in. Let's look at the region R. So the R was a circle centered at the origin, whose radius was 32/17. So if we're going to do that in polar, the R's are going to go from 0 to 32/17. And then since it's the full circle, our thetas are going to go from 0 to 2 pi. And this should make all of you much happier. Compare that to the rectangular one we saw just a minute ago, and it's no question, no contest which one we like. All right, so okay at this point. All right, so there's cylindrical. Now let's think about doing this in spherical. Now, spherical, we're going to have to think a little bit more about this. Let's start by kind of drawing a picture of it. So we know we already had the cone, right? But now this sphere isn't centered at the tip of the cone, it's off to the side. And so what we're seeing with this sphere now is going to be something that does, say, this. So it doesn't match all the way over. So the volume that we're actually looking at is going to be that volume. So think of this as your ice cream cone didn't get filled in all the way over here, but it's still heaped up over on the side. All right, so whoever's scooping the ice cream is like new to this, they're not very good. And that's the general shape that we're seeing. So the intersection, what we're seeing with that intersection is still a circle. At least it projects to a circle when we go down. So like the intersection here would be like, you totally can't see that in the red. Hold on, let me erase the red. Okay, so the actual intersection might look like an ellipse, but if we were to bring that down, imagine that we look at the shadow of this, it's still going to be a circle. Okay, so think about integration man sticking out, right? Coming out from the origin. And remember, integration man is a little bit, he's had a few too many root beers. So he can tilt, right? He tilts in all different directions, but he still is nice and straight and tall. So he paid attention when his mother told him to, stand up straight. He just starts to fall in different directions. Now imagine being in that cone. He's always going to be trapped by hitting that cone, right? He's never going to go beyond that cone. But his head is always going to be up against that sphere. So if we're going to go to spherical, first, remember that what we need is a rho squared sine phi. We talked about that last time. I'm going to prove it for you today. And then we had a d rho, let's say d theta, d phi, like it doesn't really matter. So the rows are going to go from 0 up to the top. So we need to convert this thing to spherical. All right, well, I'm going to do that over here. So for spherical conversions, the x squared plus y squared plus z squared, what does that equal? Okay, good, Victor, thanks. That's rho squared. And then for the z, that's going to be rho cosine phi, not theta, but phi. All right, now we need to solve this for rho. Obviously, rho equaling 0 makes that true, but that's silly. We need integration man to have height. So what we'll do is we'll just divide both sides by rho. And we're left with rho equals 8 cosine phi. So integration man is going to go up to that sphere. Now this sphere, its equation isn't as nice as before, right? Remember before spheres were easy, which is rho equals a number, but that's for those that are centered at the origin. All right, so that's integration man with his feet at the origin and head up on the sphere. So now let's think about, see thetas. He's obviously going to spin around in the entire circle. That'll be 0 to 2 pi. And then phis, he's going to start vertical. And the question is, how far does he go until he tips over? What is the angle for that cone? Well, to figure that out, we have to convert this guy. So let's convert that one. So z, it's rho cosine phi, equals 4 times. All right, well, we're going to get rho squared cosine squared theta sine squared phi plus rho squared sine squared theta sine squared phi. Well, you notice the cosine squared theta, sine squared theta, factor that out. That's going to be 1 times, so we get the square root of rho squared sine squared phi. The square root of that, of course, is rho sine phi. So we've got rho cosine phi equals 4 rho sine phi The rows cancel. I want to combine these sines and cosines. So let me make a tangent out of it. And so I get that the tangent of phi is 1/4, which means phi is the inverse tangent of 1/4. So in terms of the angles on phi, it's going to go from 0 to inverse tangent of 1/4. Oops, that looks like more like a 7 or a 9. Let me erase that. Make that a little bit better.
Bruce, how did you get rid of the cosine squared theta and the sine squared theta?
On this line right here under the square root, factor out the rho squared sine squared phi. So you get rho squared sine squared phi times
gotcha. Times 1.
cosine squared plus sine squared. Yeah.
Okay.
The power of trig. Okay, so yeah, so all right, so this one, of course, then is in spherical. So I would argue that either one of these is going to be better than rectangular. For this one specifically, I would have just gone to cylindrical and called it good. So maybe this is a good time to kind of address Victor's question, right? Because Victor before said, how can you tell whether you should use cylindrical or spherical? The actual answer is that you can use either one, right? I mean, you can use any of the three and it'll be fine. But there are some circumstances where one form is better than the other. So like this one in particular, what told me let's go cylindrical was the fact that this sphere is not centered at the origin. If I have a sphere and it's not centered at the origin, the equation is not going to be pretty. I mean, it's not terrible, right? 8 cosine phi is not that big of a deal, but it's not nearly as nice as when it's centered at the origin, because if it's centered at the origin, its equation is rho equals the radius, and you're done. It's just a number. So that was the first thing that made me go, ooh, maybe I don't want to do that. The fact that the bottom is a cone, that's actually a really good plus for spherical. Because look at what it ended up being the bounds on phi. It was 0 to an angle, and the angle, that's the angle of the cone. So cones in general do like spherical because those give us nice bounds. But when I was setting up cylindrical, or we even saw this when we did rectangular, we saw that the region over which this volume was circular. That's actually what told me, ooh, go to cylindrical. So I think for me, pretty much what trumps everything is the region in the plane. Once I get rid of the z, what kind of region am I looking at? If it's a circle, I go to cylindrical because the circle is going to be fast. Thetas are 0 to 2 pi, r's are 0 to whatever the radius is. I'd much rather deal with maybe some more complicated functions for my bounds on z if the remaining ones are just numbers, and numbers that are easy to find. I think finding out 32/17 was a little bit easier than finding the inverse tangent of 1/4. But again, that's my personal opinion. Anyway, so I think the answer I'm going to give you, Victor, and I'm sorry for this, is how do you know which one is depends. It really depends, but things to look for, look at the region, the 3D region and the 2D shadow. Okay, look at the region, and that tends for me to be the one that pushes it the most. But then specifically, sometimes cylindrical versus spherical, it can be what the surfaces themselves are. If they have circular symmetry, then cylindrical is pretty good. Like this does not have circular symmetry because of the fact that it's been shifted over. And that's why when we actually went and we solved for Z, it got a kind of a rougher kind of equation. But we did get lucky that the region itself is a circle. But like the bottom one is circular symmetric, right? And you saw how nice that converted. It was just 4x. And then the case for spherical is if you've got a shape that's got like 3D symmetry, spherical symmetry. That's kind of the push there. So not an easy question to answer because there isn't an answer. It's like so many things. It's how do you feel about it when you're presented with that specific integral. All right, so I think this was number 3. Did we beat number 3 to death enough? We good to move on?
Yes, we beat it to death.
Yeah. Are you feeling better? Let's see, Seamus, you were the one that asked about it. Are you feeling better about it?
I was just so stuck from just getting a z equals equation, and then the fact that you showed that we just have to do a quadratic.
Yeah.
Yeah.
Okay. Yeah, and realize that's a good trick when you've got this sort of thing, quadratic with x's and y's on the inside. Okay, so let's go take a look at number 9. See what that one looks like, since that was also a popular one. There were multiple of you who said you wanted to see number 9. All right. So we want to evaluate the triple integral over the solid B. All right, so it says here that B is x squared plus y squareds are between 3 squared and 5 squared. The y's are greater than or equal to 0, as are the x's, and our z's are between 1 and 4. I'm going to warn you here. Oh, okay, good. If I like that, this graph is an example, may not be the same. It's not quite the same, but it's a similar idea in terms of our shape. So let me do this. Let me write down these equations, and then we'll go to the whiteboard. All right. So let's, I've never been happier to hit clear all drawings. Bam. That one got messy. All right, so let's start with here's what B looks like. So we have x squared plus y squared are between 9 and 25. X is greater than or equal to 0, y is greater than or equal to 0, and the z's were between 1 and 4. All right, so I want to draw this first. Let's draw this picture first, and then we'll worry about doing the integral. So first of all, if we look in the xy plane, we've got x is greater than or equal to 0 and y is greater than or equal to 0, so we're in the first quadrant. Then I've got x squared plus y squared is bigger than or equal to 9 and less than or equal to 25. What kind of shape is that going to give me?
Ring.
Yeah, it's a ring. It's going to be the area between a circle of radius 3 and radius 5. So for this guy, right, it looks something like that. So there's 3 and there's 5. There's 3 and there's 5. So we don't have the full ring. We don't have the full washer. We only have the part in the first quadrant. Okay, so then the z's going from 1 to 4, what does that do? How does that make this three-dimensional? How about this? Where is z equal 1?
It's an XY plane.
Okay. So what we want to say is that it's parallel to the XY plane.
Yes.
Because there's only the one XY plane, right? It's parallel to it, but it's up 1. And z equals 4 is up 4. So if we were to look at this from the side, let's see if I can do this justice. Oh, that's not too shabby. Okay, so here's that quarter circle. And then we've extended it up from 1 to 4. So if we had a z-axis here, it's from 1 to 4. All right, so how are we feeling about the picture of this region?
Pretty good.
Good? All right, I'm seeing a couple of thumbs up, and thank you for jumping in there, Jacob. All right, so let's think about this one in terms of our different options. So we've got 3, rectangular, cylindrical, spherical. What do you think? Which one?
I'm thinking
Cylindrical?
spherical. Yeah, cylindrical.
Okay, a couple of votes for cylindrical. I definitely like cylindrical. Think about yeah.
Sorry to interrupt. Is this question 9?
I think so. I hope so.
My question 9 looks very, very different. Like it's not even related to this.
Ah. Okay. This is definitely my question 9. I went back and I looked at it. Let me show you. What's yours look like?
Mine is I have a spherical region. My region E is bounded above by a sphere and within a cone.
Oh.
And then Z is greater than or equal to 7. So yeah, it's not really like this.
Huh. Okay then. What? Yeah, we'll attack yours. We'll talk about yours too in a second. Oh, Eduardo's. You said yours looks different too?
Yeah, I think they're all different.
Does anybody have one that looks like mine? Just curious. If you don't know, you don't know. It's not a big deal. Okay, so Jesus, yours is like this. All right, so I guess then Jesus got lucky because he's got the one that I'm showing, but we're similar. The fact that they're different doesn't surprise me because I know that they do that all the time, right? Different functions. But the fact that it's this different is surprising to me. But let's go ahead and get this guy set up. So I definitely would go cylindrical because the region in the XY plane is very polar. And the only thing going in the Z is we're just going up and down. And so, like Victor said in the chat box, it looks like part of a cylinder. Well, if it looks like part of a cylinder, use cylindrical. All right, so if we do cylindrical, we're just trying to integrate the function z. All right, so for cylindrical, we need to put in r dz dr d theta. The z's go from 1 to 4. The r's are going to go from 3 to 5. And then what about the thetas?
0 to pi over 2.
Beauty. All right, and there you go. So this one's going to be super fast. Since the bounds are all numbers, this one you'll be able to integrate like nothing. Okay, well, yay. But that doesn't help when you have a different kind of shape. So, Seamus, can you tell me again what yours was?
Yeah, mine is the region E is bounded above by x squared plus y squared plus z squared equals 100. And it's within x squared plus y squared equals 49. Z is greater than or equal to 7. Is that kind of like yours, Eduardo?
That's exactly like mine.
Okay, cool.
All right, so did I write those inequalities down right?
Yeah, that looks good.
So
Yeah.
we're under the sphere, above this plane, and within this circle.
Mm-hmm.
Okay, so let's see if we can kind of draw this again. So we've got a sphere. Right, there's our sphere. We're under the sphere, but we're above z equals 7. So z equals 7, of course, is just a plane. It's going to slice through that. And it's going to slice through it such that there's a circle. Right? Spheres, when you slice through, you get circles. So this is like the top of the ice cream cone. Right? Like if I were to redraw that, we're seeing that shape. Yeah? So far, so good?
So far, so good.
Okay, and then we are slicing through this with another circle. The x squared plus y squared is less than or equal to 49. Okay, so let's do this. Let's think about where that circle is. Are you sure these are the numbers that you had?
Yeah, 7 squared is 49, right?
Yeah.
Yeah, that's it.
On mine, it gives me theta is between 0 and pi.
Instead of,
No, also including all that stuff.
oh, okay. So then you're only going to do half of it. All right, well, here's what I want to do. I want to figure out this circle right here, the green circle, so the one that forms the bottom of this. If I let z equal 7, that's going to give me x squared plus y squared plus 7 squared equals 100. So x squared plus y squared equals 51. Okay, we're good enough. Never mind. I was concerned that the region that we were cutting through it was bigger than the region itself, but it's not, because this green circle has a radius of square root of 51, which is bigger than 7. So what we're doing is we're going to come down through this with a circular cookie cutter, So our shape is going to look like that. Let me redraw that line.
Yes, to clarify, the cylinder is smaller than the circle cut.
Correct.
Yeah.
Correct.
Okay.
The green one is the circle x squared plus y squared equals 51. The cylinder is x squared plus y squared equals 49. So the circle that's on the bottom of this is x squared plus y squared equals 49. This is z equals 7. And this is our sphere. Whoops. Might help if I spell it properly.
The Shapir.
Yep, Shapir. It reminds me when I was in elementary school, you know, when you get the class photos taken, so your entire class together on the risers, right? And they had a little sign that said, you know, Foothill Elementary School, first grade class, whoever, right? One year, they botched this for every single one. They spelled school wrong. They spelled it SHCOOL. So I went to Foothill Elementary Shakool, which was really Shakool. And I still think that's pretty amazing that a school that's all about educating people misspelled something that I think I still have a copy of that somewhere in a file that my mom kept. So anyway, we don't have a Shapir, we have a sphere. All right, so this is our chunk that we need to integrate over. Okay, so you've got whatever your function is. I don't really care what that is right now, but let's think about this one. How do you want to do this? Do you want to use rectangular, spherical, or cylindrical?
Cylindrical.
Cylindrical.
I definitely agree cylindrical, because if we do cylindrical, so we'll have insert your function here, right? It doesn't really matter, but we're going to do an r dz dr d theta. The z's are going to go from 7 up to the sphere. Well, the equation of that sphere is going to be the square root of 100 minus r squared. Right? If you take this equation, solve it for z, you put r squared in for x squared plus y squared. But there you go. There's that. The r's, the region that we're looking at because of our cookie cutter, are going to be r's from 0 to 7. And then the thetas are going to be 0 to 2 pi, unless you have like Bradley's. That was you, Bradley, right? That said you had a different thetas?
Yeah,
Okay.
it's from 0 to pi.
So then you would just go, well, instead 0 to pi, and then we're only cutting through with half of that cylinder. So this is another one that I think cylindrical definitely would work out better. Because imagine trying to do this spherical. What's the issue with doing this guy in spherical? I mean, with the other one, we saw like we didn't even want to think about spherical. But this one you might, since the surface, the top here is spherical, is a sphere. Why might you not want to do this in spherical?
Because aren't we going to have to find where this imaginary cylinder intersects the sphere?
Totally. Because if you think about, so down here is the origin, right? And you think about integration, let me bump him up so he doesn't have to be quite as tall. So integration man is going to go out along radial lines, but some of the radial lines like here are going to hit the side. They're going to hit the cylinder. And other times they're going to hit the sphere. So we would have to figure out what angle is this, where we switch from being on the sphere to being on the side of the cylinder. And that, if we go back to my how I decide, that right there immediately makes me go, nope, not doing it. I would only do spherical here if nothing else was a viable option. Meaning, the only way I'm not doing this is if this function is such that I literally cannot do the integral. Right? Like if the function was e to the z squared, I'm screwed. I can't integrate that. Then I would have to go to something like spherical. But barring that, I am not touching spherical. Not to mention that his foot is not a super nice function. Right? Integration man, I guess I didn't draw integration man very well there. Because integration man's feet are actually inside, right? So forget about all that stuff. His feet are always on the plane, z equals 7. And z equals 7, I'd have to convert that. It's not terrible, but it's going to be rho equals 7 secant. Yeah, 7 secant of phi. But then going to the side, having to convert x squared plus y squared equals 49 into spherical. Again, that's a whole lot of nope. All right. So I guess there's a version 2 of number 9 to go with version 1 of number 9. I'm just curious, does anybody have a third version? I'm not necessarily going to do it, but anyone have one that's significantly different from these? Like Bradley 0 to pi, I wouldn't say is significantly different. All right, well, not hearing anything, I'm going to go with it. Yep, they're all similar to one of those at least.
I have a quick question for you.
Yeah, sure, go for it.
Is there a conversion between cylindrical to spherical? Or I guess it would be more like polar.
Yes, there is.
Okay.
Do you want to see it? No.
No, it's okay. I was just curious if there was.
Yeah, I'm going to clear this real quick. I can show you real fast. So when we're going, you're going from r theta z, and you're going to bounce back and forth between that and rho theta and phi. Okay, well, the theta is the theta. So there's 0 conversion there. For the z, it's the same one as the conversion from rectangular to spherical, because that z is the same. So then if you want to go from r into the other one, so r, think about how r is the square root of x squared plus y squared. So r is going to be the square root of rho sine phi cosine theta squared plus rho sine phi sine theta squared, which, if you just trust me, gets you r equals rho sine phi if you do a little bit of trig identity work with the thetas. And so those are your conversions. They're actually not bad, because 2 of them we already kind of had. The third one makes sense if you think about the picture. All right, so we're somewhere out here. There's rho, here's phi, there's our z, and this side's actually our r. And so you can see how the sine of phi is r over rho, which gives you that. So, anyway, so the answer is yes, there are conversions, and there they are. You actually already knew most of it. You just didn't know it. You didn't know that you knew.
Thank you.
Yeah, you're welcome. You can also do the same thing, like, you know how, for example, we had the rho squared equals x squared plus y squared plus z squared. Well, that tells you that rho squared is equal to r squared plus z squared. So if you were given r and z, You could use that to find rho. Again, you already know the thetas. But if you want to find phi, you would just use the fact that cosine of phi is equal to z over rho. Right, so that's going the other direction. But it's stuff you already know. And like this guy, the rho squared equals r squared plus z squared. Notice that that's just the Pythagorean theorem on this triangle. Like all of these conversions come back to the Pythagorean theorem, every single one of them.
So yesterday in my public speech class, it was an informative speech, and I showed people that triangles and circles are the same.
Sweet. Love it.
And no one argued with me. Not one person.
Well, that means that you're actually a very persuasive speaker then. You had your information, presented it well, and made it, or you just like went over everybody's head that they just smiled and nodded,
It's possible.
which is how I feel sometimes in class. But I've learned in public speaking, as long as you're confident, yeah, dude, easy there, Matt. You're new to me. You don't get to make those comments yet. No, in public speaking, I found that the key is to be so confident that you, no matter what you say, it sounds convincing, right? And I don't pull this on you guys. I'll be the first to tell you if I don't know, right? Like you'll ask me something, I'll be like, I don't know. It's a good question. But if I wanted to, I guarantee you I could bullshit my way through any question you have about calculus, because I would start throwing in things like, all I'd have to do is go, well, if you use the epsilon definition of the limit and then you apply it to triple integrals, but now you need an epsilon and a delta, but also a gamma, right? Okay, so what happened to all you guys?
I was
Right there.
believing you already.
You're like, yeah, that sounds okay. So first of all, there's no bullshit gamma thing. There isn't, right? But you were like, okay, sure. If there's a delta and an epsilon, why not a gamma? But yeah, it sounded convincing because it had enough ring of truth to it, sprinkled in with a little bit of, well, I mean, I know this stuff and you don't know it yet attitude, right? And I know that attitude comes out from me, even though it's never like a, you guys are nothing. But I mean, it's true. Obviously, I know more about math than you guys do. And so I'm sure that comes across even unintentionally, right? But you mix that with just like words that sound right. And, I just throw in the phrase every once in a while. Well, and, when you get to, real analysis as a math major, you'll start seeing this more. I throw in something like that, then you all go, oh, okay, right? So I am not the kind of person, like I would be a bad politician, not because I'd be a bad politician as in I'd be bad, because I would totally work over people left and right by making it sound like what I want is actually positive for them. So it's probably good I didn't go down that path. We have enough of those kind of people doing politics. Anyway, I apologize for getting spouting off there, but I don't even remember where I was. Oh yeah, I was talking about your speech there, Bradley. So hey, I'm proud of you, by the way, for choosing that as your speech topic. And check this out. Like we're talking about three-dimensional stuff, and it all comes back to triangles yet again. I'm telling you, man, trig is amazing because it is everywhere. If you want to see it, it's everywhere.
Yeah, it blows my mind. I had 3 different ways to prove it to them too, but they only
Nice.
got to see 2 of them.
And that was enough. Oh, and by the way, Matt, I was just giving you shit. You can give me crap all you want. I don't mind. So, all right. So I guess we're good with homework, right? We ready to kind of talk about what do we do with other transformations in general? Yeah, no, maybe so. All right. Well, let me stop my share here. All right. Oh man, we're down to just half an hour. Actually, you know what? I think we're going to call it here. I could start into this, but I don't want to go very far. We couldn't get very far, and I don't think we get to a point where it's making enough sense. So here's what we're going to do. There is going to be a quiz next time. All right, we're going to be back on schedule. I gave you last week off as I forget what it was, early Halloween, early Thanksgiving, early insert your favorite holiday observance. So we had 1 week off, but we are going to go back to quizzes. The quiz, let me grab my book again so I can see what sections I want this to cover. Give me just 1 second here. Okay, so actually, let's make this one. The last exam, did the last exam have double integrals on it?
Yes, but not in
just the
full.
start, right? Just the
Yeah.
start?
Just
Okay.
rectangular.
Okay, that's what I thought. So let's make this quiz on 5.3 and 5.4. All right, I'll put a message up in Canvas so that this is written down, but 5.3 and 5.4, which is the section on polar, double integrals and polar, and triple integrals. So these triple integrals will not require cylindrical or spherical. If you feel so inclined, if I give you one that you feel would be better if you are using one of those and you're confident enough in doing it, feel free. I'm not going to have any that just say, do this integral in rectangular or do this in polar, right? I'm not going to do that. This is going to be more of a let you decide which way you think feels better. Okay, so 5.3 and 5.4, polar coordinate double integrals and general triple integrals. Okay, so that's what the quiz will be on. So the quiz will open up at 1 o'clock like normal, and will be need to be turned in. What do I usually tell you? 1:30, 1:40, 1:40, I think, right? I'm getting my class times confused. Whatever the syllabus says, whatever it usually is. And then as soon as that's done, we'll come back into class and we'll look at what happens if we want to do any kind of a transformation. All right, so that's the plan for Friday. Questions on that? Okay, so hearing none, let me go ahead and stop the recording.